Here we're going to look at an example problem that illustrates all of the vectors of interest for two-dimensional motion along with the manipulations of those vectors and the labeling of the vectors that we need to understand for all of the two-dimensional problems that we're doing. So let's take a look at what we have here. In the first part, we are asked to draw in the position and velocity vectors at points A, B, and C. To remind you, the position vectors always start at 0, 0, even if the trajectory itself crosses the y-axis at some other point. Position vectors, RA is a vector. Vectors have arrows. Do not lose points because you are not putting arrows on your vectors. The position vectors are arrows from the origin 0, 0 to the point in space where the particle is. The velocity vectors are always tangent. So put in your best estimate of what a tangent is. And at this point, I often have students ask, well, what if my version of tangent isn't quite the same as what you're showing there? What if I thought it was a little bit on the downslope and I drew this in? As long as you will let the grader know that your intent was tangent, so I will ask you to write the word tangent in next to your velocity vectors. You will not lose points if the grader knows that your intent was tangent and your estimate is different than what the answer key rubric shows. Okay, so part B, draw in the displacement vector from A to C. Well, that is simply the arrow that goes in a straight line from point A to point C. Put an arrow on the end, label it delta R. Please do not forget to label your vectors if the question is asking you to draw these vectors in. Now, part C, it says, off to the side, draw the change in velocity vector in. So here we have a manipulation to do. We have to do the vector subtraction. V final minus V initial. We have V final is the tangent velocity at C minus V initial, which is my minus V initial vector over here, my purple one. So I'm going to do a final minus my initial here, and I am going to get my delta V vector put in, and that is the manipulation, the subtraction I need to do to get my delta V. Now the last thing you need to do is to be able to put in the acceleration vector, and for that you want to show the grader that you understand the acceleration vector and the delta V vector will always go in the same direction. So I am going to ask you to draw in what is called the line of action of the delta V vector, which is nothing more than taking a ruler or a straight edge, putting in a dashed line as is shown here, extending the delta V vector. The A vector must, because it's an equality, point in the same direction as the delta V vector. Now the value, the length of the vector, does not have to be the same because the delta t, being big or small, will affect the actual acceleration value. Small delta t would be a big A value. So there you have it. So please make sure you understand how to draw in and label all of these vectors, and you will be in good shape.